just get that bit sorted. Very good.
Guarda, vuoi vedere? C'è Luca che organizza queste cose.
Mm-hmm.
E qua Lucasino.
Mm-hmm.
Ciao Ge. You have the microphone on. I think this is YouTube or something. Making us.
Okay, so if we're ready, then I think we'll get started. Thank you for joining us today. This is a seminar by the Commission on Volcanic and Igneous Plumbing Systems, and we're very welcome to join you with our presentation here today, which I'm just going to briefly introduce the aims of the Commission. So the Commission aims to provide a forum for volcanic and igneous plumbing systems research, which goes beyond disciplinary or methodological boundaries, and to foster an integrated understanding of magma transport and storage in the crust. And so our seminar today is one of the ways that we're hoping to achieve our aim. But I wanted to introduce the committee. So these people have been on the committee for a few years now, so there should be regular faces. But actually I wanted to introduce some new people. So Paula, Caitlin and Keris, who've just recently joined our team and our blog editors. So please get in touch with them if you have any ideas on contributions you want to make to our blog. And then also our new website and social media team. That's Gabrielle, Chelsea and Andres from the Universidad del Norte in Colombia. And so they're looking after all our communications on social media and updates to the website. So if you have any tweets that you want to get put out by the Commission, please get in touch with them. So that's a little bit about us and the committee. But when you signed up for the seminar, we asked you a few questions about things like your gender identity, your place of residence, and your career stage. And we thought that that was quite nice to share with you. So we have a little bit of understanding about who's in the audience today. So I put up a few graphs there for you to have a look at. And it's really great to see such a diverse audience from around the world and to welcome so many students here as well. So throughout the seminar, you can write comments in the chat on Zoom or on YouTube, or on Discord. So these are ways that we can get in touch. And it's our first live broadcast on YouTube. So welcome to you who are watching on there. Okay, so I will pass over to Chiara Montagna, who's going to introduce our speaker for today.
Yeah, so welcome everyone to our second seminar of this series. Today, Eleonora Rivalta is going to present us what pathways for ascending magma, implication for geophysics and petrology. Eleonora is a senior scientist at the German Research Center for Geosciences in Potsdam and professor at the University of Bologna in Italy. She got a degree in physics in Bologna, after which she spent some time doing postdocs in Hamburg and Stanford, and she went to Leeds as a lecturer before finally settling in Potsdam with an ERC research group focusing on the mechanics of magma propagation by diking. Together with her students and postdocs, she has developed analytical, numerical, and analog models of magma propagation under the influence of crustal heterogeneities and the external stress field. Recently, she's focused on explaining and forecasting the location of intraplate volcanism and, at a smaller scale, of eruptive fissures and vents. So, Eleonora, up to you.
Thank you so much, all of you, for this invitation and for this nice introduction. I will go straight to the presentation. Okay, so today I'm going to focus on presenting, explaining how magma can propagate very long distances through rock by becoming a very sharp object. Here I put a razor blade and swords and stone, and becoming a very efficient way to just bring magma to bring itself, propel itself to the surface to erupt. Oops. Yeah, so I will focus today on a particular form of transport of magma. There are others, which is diking, and in particularly also on big dikes. Typical volume of dikes are between 1 million cubic meters and a few cubic kilometers, although in the geological history, we can go far beyond this. They travel distances of up to several hundreds kilometers. Here on the right, there is an example of kimberlite magma bringing diamonds to the surface, and their velocities is up to a few kilometers per hour. This makes this form of transport very efficient, meaning that the vast majority of magma that reaches the surface was either contained in a dike or is being transported through a conduit that was originally formed by a dike that has pierced the surface. So therefore, it is a very important way to, it's very important for us to better understand. So this is the motivation of my talk and my research in general, how can we better understand and forecast even magma migration in terms of location, velocity, timing, and even volume rate. I will go through the methods I use, in particular how we can constrain stresses and use fracture mechanics, and then finally also consider magma properties to achieve this. And I will go over the implications. So what do we expect in terms of crustal fabric? So how does magma then modify the Earth's crust? And also what are the implications for the evolution of magma chemistry before discussing future plans, needs, and opportunities. First, I will go over a few observations to just focus on a few points that I would like to stress on. So I will start with this. So I will go over recent dikes, and I'll start with the Bardarbunga whole round dike, which all of you know. So this dike propagated from the caldera of Bardarbunga, from below the caldera, through a tortuous path to erupt in the plain of all around with this lava flow and creating a lava flow. The dots are earthquakes caused by the dike, a cloud of earthquakes accompanying the tip of the dike. And the color is day from the start of the episode, the 16th August. This tortuous and segmented path was explained by Sigmundsson et al. In terms of a competition between topographic load stresses and tension at the plate boundary. This explanation was a beautiful application of a line of research that is older than that, and of which here I put just a memorable example for me, the paper by Romano and Gepard in 2014, but also others, of course. It's the topic I'm going to expand on today. So first of all, I'll go straight into the things. I will not just go around it. What controls magma trajectories? Stress. We know the answer since 100 years almost, mainly through the research of Anderson, which at the beginning of the 20th century, from field evidence, figured out what controls the orientation of faults and also dikes in the field. So we know that when propagating magma makes its own pathway by creating a dike, and that these dikes orient roughly perpendicular to the least compressive stress axis in this way. And they are therefore at their preferred orientation or optimal orientation is not the same as faults. And this is the reason why they usually do not occupy faults, which are mostly inconveniently oriented. And they also don't need any weak spot or pre-existing conduits. Dikes are sharp objects and can easily fracture through the hardest rock. So for people who are not very familiar with the concept of stress, I thought maybe there could be some petrologists or some people who are not familiar. I will just make a brief introduction because I will use this concept. So if we apply some stress to a volume of rock, it will deform. We can define principal stresses, which are our most compressive, least compressive, and their direction, the principal stress axis. So as we said before, faults will be oriented in this way or in this other conjugate way in the field in this particular directions that I plotted here, while dikes will be mostly perpendicular to sigma 3. This is very useful principle because it helps us understand a lot of things, regarding volcanoes. And I'll put only one example, but this is ubiquitous. So this is the East Rift Zone of Kilauea. The East Rift Zone has a flank dynamics that brings the flank to slowly or sometimes episodically slide towards in seaward direction. This creates a stress field that is conducive for dikes to just align perpendicular to it. By doing this, they also push the flank. So therefore, you create this kind of feedback effect that is also ubiquitous with different flavors in many volcanoes around the world. So this we understand, but there are also things we don't understand very well. So for example, what is not yet explained, to my knowledge, is the creation of many fissures. So the lava flow that the eruption in 2018 that is the largest since many decades at Kilauea was started by many fissures. So, and they opened in a mysterious sequence starting from number 1, the number 2, number 3. They jumped back and forth before establishing themselves in this fissurate that then generated most of the flow. This matters obviously because it was in a inhabited area, and this can happen. So we would like to know why one fissure is not enough and the dike needs to open another one at some other location. And in the first place, where the first fissure is going to be is also an important point because it may really make the difference between an area where you have houses and people and an area that is not inhabited. So I will go to the most recent dike, which is the dike in the Reykjanes Peninsula, which also obviously intruded in a stress field that was that is prescribed by tectonics and not only tectonics. So here we see in this paper by Clifton and Cattenhorn in 2006, previous fractures and faults and fissures in the area. So in this paper, strike slip faults are red, don't confuse with eruptive fissures. Fissures are yellow and normal faults are green. And we can see that strike slip faults tend to be north-south, while fissures at an angle of 20-40 degrees with respect to them, normal faults mostly aligned together with the fissures. So this can be explained with the principle we mentioned. These fissures cross-cut each other in the field. They also have interaction. You can see that the fissures create some stress and the faults orient to the stress of the fissures a little bit, so you can see at the tip, but this is a local effect. The big pattern is simply quite regular, and it may be a little bit misoriented with respect to the tectonic extension, but as we will see, tectonics is not the only source of stress. So we need to go after the overall stress in order to understand our dikes. Anyway, this 2021 dike simply did what was expected from it according to the previous patterns, and created its fissure, and in spite of having a strike slip earthquake relatively large and very close just in the days before, it didn't occupy it. But we know this because we know that dikes don't really care about the misoriented faults, and they want to create their own path because they are sharp. They don't need any previous fault to propagate. Also, this dike opened a series of fissures, so it was erupting from the vent system number 1 here, and then it at some point, unannounced, one could say, opened another fissure here in this location, and then it jumped 3, then it jumped 4, 5, 6, and created a series of fissures. It is obviously important to know, like IMO, when they saw this, they simply said, okay, please avoid the whole area above the dike because you can, there can be unexpected lava flows, but it would be good to know where the first eruption is going to start. And during the talk today, one of the things that I want to present is that I think we are close to answering this problem. We are now close. There are also very weird, sometimes, pathways of dikes that surprise us. And I think this is one example, like the weirdest, at least that I think has happened recently. It is the 2018 dike at Sierra Negra. And this dike stayed flatline, stayed horizontal, went down the flank of Sierra Negra, and then turned to the right with a 90 degrees turn here before erupting in a fissure here. It had opened all along the way many fissures, and still it decided to carry on and do this weird thing. So what about our principles of orientations according to stress and so on? I will come back to this later. So before going to the modeling, I would like then to make a short summary of observations. Before erupting, magma may travel many kilometers vertically, diagonally, horizontally. Pre-existing faults or conduits don't guarantee that magma will take that pathway. Magma will decide itself whether it's a convenient pathway or not. Generally, it is not. Most eruptive conduits, anyway, are pieced open as a dike first and later evolve into a conduit. And vent location contributes substantially in determining the hazard and the risk. Therefore, it's something that we would like to forecast. And if we want to make sense of these observations, we need to understand even more deeply the rules of dike propagation. So I started with this sharp object concept, and here I put many of them so that this sticks to the mind. So dikes are transported by a mechanism that is very similar, or is hydraulic fracturing. So dikes, this mechanism can be active at very, very wide spatial scales, from small veins in the field to super large and long dikes like this in the British Tertiary Province. it's also used the same concept in the industry, because by injecting water or brine or any fluid, gas at high pressure, we can fracture rock very efficiently and increase permeability and use this for industrial applications. So this is just one simple gelatin experiment, just to show that dikes actually get this shape, which is this inclined tadpole shape. This dike in particular is also inclined. So here the concept is that dikes can be pushed by a magma chamber. Like in the industrial setting, you really push water at high pressure to fracture. But this is not obligatory. Dikes can also self-propel. You can see here that the injection just propagated by itself without any additional flow. You need two things. For this, you need to, first of all, have a gradient in the stress. What is a gradient? Here, the gelatin, the weight, lithostatic weight of the gelatin is increasing with depth. And in the column of air within the dike, this is an air injection, the pressure is increasing with a less steep slope because it's air, so the weight is not that much. Therefore, it ends up being pressured very much at the tail and closing, and all the fluids accumulates at the top and has a higher pressure. This is what makes the shape like this, and we will see how and why this shape is particularly good for becoming very sharp, so that it can self-propel. So normal stress gradient in the stress example like before, simply you have your dike oriented perpendicular to your sigma 3 axis, which is the least compressive. As normal stress would be when this sigma 3 has a gradient. A gradient means a variation along distance. Okay, so then the shape of the dike becomes this one. And now I will go, okay, this can also work. It can be buoyancy pressure, where you have the weight and the magma pressure inside and the external lithostatic pressure outside, pushing differentially and squeezing the dike like a toothpaste up. But it can also work horizontally, where you have the highest part of the volcano, the topographic load, squeezing more efficiently the tail of the dike, so that the dike decides at some point to walk down the flank like this. And this generates these shapes, which are the same shape that I described before, but just horizontally. You see it in map view when you go to the field. Okay, now how can we use this? It's going to be very simple. I will not go into the equations because they are complicated, but I want to explain the concept of stress intensity factor, because it is a very good way to explain how dikes can become that sharp. So stress intensity factor is illustrated here. Here we have the fracture. Inside the fracture, we have a pressure. Here in this plot, the pressure is negative. It's compression negative, while extensional stress at the tip is positive and goes to infinity, because there is a singularity there at the tip of the crack. And here is the stress illustrated by this shading, red shading. So the stress intensity factor is a combination between the height, how high is the stress at the tip, but also how it decays away from the tip. You can see that the unit of the stress intensity factor is Pascal per square meter. So the square meter here describes exactly this going away from the tip, because when you want to extend a fracture, it is not enough that right at the tip you have the stress overcoming your threshold, but you also need to keep up the stress for a little bit in order to really extend the fracture. So the stress intensity factor describes this, and it is a very handy quantity. It is equivalent to a more physically elegant quantity, which is the elastic energy or energy release rate, where rate is meant again as the fracture extends, not in time, but in length. So now, if you have a gradient inside the crack and you have the dike gets this tadpole shape at the bulb, at a bulbous head, then you change the curvature here, and by changing the curvature, you so you have the gradient here in pressure, the curvature is changing, and the stress becomes higher, both in terms of value and also how it decays. So this makes it very sharp. If the stress intensity factor is higher than the fracture toughness of rock, which is a rock parameter, although this is also a complicated issue, then the dike will become very sharp. And this happens when the dike gets a critical volume. It happens when the dike reaches a critical volume for the gradient that is subjected to. So here I have this one equation, which is this critical volume in 3D. So here we have elastic parameters, Poisson's ratio, shear modulus, we have this fracture toughness, and then only the gradient. This is the gradient to which the fracture is subjected to. It is a combination of this delta rho g, which is this buoyancy gradient, times sine of theta, because we also, this is a gravitational thing, therefore it is important. So it's more efficient if it's vertical. If it's horizontal, this goes to completely zero. And then we have the external stresses, which are this derivative here. I write the derivative or gradient of the normal stress with respect to the coordinate of advancement of the dike. Obviously, this was shown in the graph and everything in 2D, but actually it's a 3D thing. So the dike will have a piercing edge. Actually, it will fracture rock at the piercing edge and gets shot, or at least partly at the tail. This is the frontal view, and this is the side view. If we look at it from the side view, and this is like in 3D. We need more 3D models, but I will come to this. So how can we model and forecast magma trajectories? By using these principles. So we remember the principles of Anderson, of principal stresses and orientation, plus what I just discussed, which is fracture mechanics. First, we need to constrain stresses. So volcanic edifices have a very complicated stress state because they grow, they are consumed by various processes. You have collapse. Most of these processes are actually boil down to gravity in the end. Anyway, we have edifice load. Actually, I start from the biggest and I go to the smallest. Biggest scale, smallest scale, it's important, and I'll come to that later. Bigger scale, tectonic, because it's everywhere. Tectonic stress is from the very surface to the bottom of the lithosphere, you have it. Edifice load is the second biggest generally, because generally volcanoes may have a large edifice, not all of them have. Then you have excavations. Excavations is when some mass was taken away by whatever process, a caldera collapse or a landslide or something. Generally, this is second degree. So after edifice load, you have excavations. Calderas have large excavations and not a big edifice load. And then you have other things like flank collapse. You have faults and earthquakes. You have magma reservoirs and dikes. So I just remove this to make the ones that are bigger scale highlighted here. And now I will go on to say why I deleted magma chambers. They are generally very much looked into in terms of stress. But here I want to make the point that actually they are lower priority than other components, much lower priority. And I will show it to you by some stress calculations that I did with some functions, MATLAB functions that are available and everybody can do and verify. So this is a magma chamber, ellipsoidal in shape. This is not to mean that I think magma chambers are ellipsoidal in shape, but we can discuss this later. Anyway, for the stress, this is a convenient shape to take. And you can see that the principal stresses, if you see like this cross with a circle, they are parallel to the screen and therefore radial to the magma chamber. If you see a segment like this, they are perpendicular to the screen in that direction, oriented like this. So here is if only the magma chamber is present, but now I want to compare it with the edifice stresses. So here I put a very, very tiny edifice of 2.5 kilometers diameter and only 500 meters height. And you can see that it has already a little stress to it that if added to the magma chamber, already completely changes the pattern. Only close to the magma chamber, you keep the same pattern, but far away from it, the volcano is absolutely dominating already. By the way, I didn't say the magma chamber here, the pressure level was 5 megapascal. Obviously, it could be a bit more, but anyway, the directions all point towards the volcano. So volcanoes attract all the dikes. Then if you increase the edifice, both radius and height, the stress becomes more intense, more intense, more intense, until the magma chamber, really, you almost don't see it. Obviously, if you zoom very carefully and you go very, very close, then the stresses of the magma chamber are still there. And they are important to decide the point where the dike will breach, for example, on the magma chamber, where exactly the dike will breach. But as soon as the dike is a little bit far away from the chamber, the stress field that will command it and drive it will be the edifice stress, if you have such an edifice. This is Etna size, just to make an example of how big this is. Also, I plotted some colors, which I didn't comment on. The colors are the sigma 3, is the contour lines of sigma 3. So you see that actually you go, if you are a dike, you're here and you want to rise, you go against a much bigger compression, which will squeeze your tips and change your shape in the less sharp direction. You will become non-sharp. And therefore, there is a chance that, a big chance, that the dike will get stuck. Anyway, so this I already said, that there is nothing of the original magma chamber stress when the volcano is even big size. In general, we need to ourselves, going maybe size after size, tectonic, loading, unloading, go over the stresses that we think are important for the specific case, because every case anyway is different, and superpose them to have our stress field. The problem is, very often we don't know the relative weight of these components. So this is my most recent paper, where I explain a method. For now, it's more a principle than a really application, but we are working to apply it so that we can give bent maps. So this paper describes a method to really calibrate all the stress components so that in the very end, it can be predictive for magma trajectories. And how does it work? For example, by guessing the relative components, calculating all the trajectories and checking whether these trajectories really bring the dikes from the magma chamber to the vents. If they do, then we improve this. We improve in a circle with grid search, optimization method, whatever, until we find the perfect stress field that really brings the magma from the magma chamber to all previous vents. This is the optimal stress field. And this stress field I can use easily then to calculate stress maps. And this is and the future vent maps. We tested this in gelatin by creating gelatin dikes and then changing the stress field by applying extension or filling up the caldera with water to see if we could predict the future dikes injected in the gelatin. And this works very, very well because trajectories are very, very sensitive to the ratios between stresses, like here, excavation and extension. And if you constrain it with just a few trajectories, then you can really forecast new trajectories if you know where they start from, for example. Now I will go to the lithospheric scale to see whether this principle can also help us understand observations, in this case, geophysical observations, at a much wider scale, not just a local scale at the volcano. So this is the Baikal Rift from Tuvenis in 2009, and what they saw with a seismic reflection study. they saw that the lower crustal seals, intrusives here, and so one could ask why do we have intrusives there and why and crustal seals? Also, why are actually the lava fields not at the rift, but they are completely far away? They are very distant from the rift. Another completely different observation. So here we are in extensional tectonics and with an excavation. And here we have the completely different opposite case where you have compressional tectonics. This is Mount St. Helens, this volcano here. And below Mount St. Helens, again, flat-lying seals are seen at a depth of around 40 kilometers, so actually quite similar. Can we use these principles that I described before also to understand this? So if you do the stress models, you find out that actually if you create an excavation like here in the Lake Baikal, in the graben below the Lake Baikal, if you model this and you model some tectonic extension, you find that your dikes really can't manage to stay straight here below. They need to be flat lying because the vertical is symmetry is vertical. They don't manage to be vertical. If you inject them vertical, even they turn. And then they ascend very obliquely until they emerge far away from the rift at the rift shoulders. And this would explain both the lava field, the orientation of the intrusives, although we don't see in the data these curved pathways, but this is because reflection seismics really sees only very well horizontal things. So I would be curious it would be nice, it would be cool if methods could be developed that can also highlight curved pathways and not just horizontal. Let's go to the Mount St. Helens. And if you do a model here, I took an old model by Thorsten Damm, where you have compression and then you have edifice loading. And the compression, so the edifice loading is dominant down to a depth, more or less like the diameter of the load. And then below that, you see only the effect of the compression. So you have horizontal dikes below a given depth. Here you need to rescale it and you really find something similar to here. And then above, you find vertical pathways. So again, here we see the horizontal ones, but we cannot see the vertical ones. So in order to really prove this method, prove this model, one would need to see if there is any way to highlight vertical pathways. This same concept is being used by Sara Oliva now to explain focal mechanisms that are misoriented in the East African Rift to the tectonic stress field. They are misoriented, and she's now using a similar technique to see if this can be explained. I will have now a very brief discussion on petrology. This is not completely developed yet, but I think I'll make a point. So let's go back to the loading map and also to an unloading map that it's in the vent forecasting paper. So I said already, if you are a dike and you want to ascend, you will have trouble because the compression will increase and increase and increase. So basically what you would expect for such a big volcano is that most dikes would get stuck here at the bottom of the volcano. The opposite, no, not the opposite, the completely different things would happen for a caldera. So you have unloading and you have vertical sigma 3. So actually here also they get stuck, but for a completely different reason. Here they get stuck because they are, even if they are vertical, because they are, their tip becomes very compressed. They would need to be very big to really pass through. Here they get stuck for the reason that they are horizontal and they completely lose their buoyancy. So here the reason is more the external. So the external stress determines the orientation, but also determines the gradient of the normal stress. So there are these two things, orientation and gradient of normal stress. Here orientation is enough because you just are flat. So what happens then? it happens that in this case, for example, you would have a system of stacked seals and later form a very big magma reservoir. And you would also, what could this model predict is that if you have any magma pathways that manage to come out from a lower level, they would have a different composition. They would have a more primitive composition, because I understand from geochemists that deeper levels are expected to be more primitive composition and emerge at a lateral distance. So a bit more external to the shallower paths. So therefore you would see in calderas composition that goes from very evolved to very primitive as you go away from the caldera, as you go away from the center of the caldera. While for stratovolcanoes, you would expect vertically elongated magma chambers that erupt very frequently, because if you think here that you have the same supply rate, this phi is a supply rate. For the same supply rate, here the problem of these dikes is that they just need to become, they are buoyant, they just need to become a bit bigger, and so they would erupt frequently and don't change their composition very much. Well, here for the same supply rate, you would need to bring a massive amount of volume before for horizontal dikes with no buoyancy to be able to ascend. So actually, we can compare this to observations. Like at Etna, you see vertically elongated system, at least from crustal deformation. This is what you see, both at the bottom and more shallow in the volcanic edifice. And we see frequent eruptions, and we see primitive magma chemistry, while in calderas, we see peripheral eruptions that are more primitive. More work is needed to just follow this idea and really prove it, more work. By the way, Marco Neri told me that at Etna there was a phase when there was a caldera thousands of years ago, or maybe even more. And during this phase of a caldera, there were pyroclastic flows and much more evolved chemistry. So this going into the history of the volcano could help bringing a point here. Okay, just now I will go to 3D magma propagation, and I present very shortly a paper that is now under review by Tim Davis, my PhD student, who is going to defend his thesis at the end of this month, very soon. So he created two methods for 3D dike propagation. One is based on a disk that you simply evaluate on the disk edge what is the stress intensity factor, and then you find the direction of propagation according to that. And he applied it to Sierra Negra. Also, he did a fully 3D method based on triangular dislocations where you have even an evolving tip line, where the dike has an evolving tip line, and here where you see that it is red, it means that is the sharp edge cutting, and blue it's not cutting, and gray is closing down. So the answer here for Sierra Negra is simply that the dike was so close to the free surface that it was a very strong influence of this free surface, a very shallow path, and a big contribution of buoyancy, so that the dike went straight down the flank. But when the flank became too shallow and flat, then the buoyancy became more important, and probably simply a starting tilt of a very few degrees would bring the dike then to the surface in this direction. I want to point out that obviously I didn't comment very much at all on geological heterogeneities, density heterogeneities, magma properties. So we know that geological heterogeneities make a big difference, and there is a lot of work done on this. I'm very sorry that I cannot expand on this very much because the time is limited. Density heterogeneities are very important both in rock and also in the magma, because they determine this buoyancy force. They are fundamental. to decide whether a dike will propagate or not. And please check wonderful work by Meredith Townsend on this topic. And obviously magma properties are very important to be checked, and only when we have integrated very well these topics, we can go to another point, which is the velocity of the dikes. I didn't comment on the Bardarbunga, but the Bardarbunga dike was had jumps in velocity, was going fast. Here is distance, here is time. So we see that it was propagating fast and stopped, propagating fast, stopped, propagating and then stopped again. If we want to understand this, we need to combine the stress models, because we need the direction. Otherwise, we don't have the gradients, the stress, the normal stress, we don't have anything. We need first to figure out the direction, and then we need to run a proper fluidodynamic models on the dike. There is this paper by Virginie Pinel in 2017, and Virginie, she's working with Francesco Macaferi and Severin on bringing this model to a new level. So check also that. This is my conclusions. Dikes are sharp objects. They can self-propel. They don't need a magma chamber pushing them. The dike pathways reflect the in situ stress, which we need to figure out. Dike paths may be curvilinear, inclined, according to this stress. And they also can contribute to affect the magma chemistry, especially when they get flat lying in the volcano, or when the surface loads are a hinder to the further propagation of the magma. So in conclusion, we need very well calibrated stress models, and we need fracture mechanics if we want to model and forecast the trajectories and the opening of future vents. These 3D models that I showed by Tim, I think they are applicable also to solve the problems of these many fissures opening in these weird sequences. This is very close now to happen. They can help, all these models can help understanding the magma propagation by diking at lithospheric scale, which I think occurs still by diking, and therefore this is, I think we should go into that direction as well. And also to understand possible external control of magma chemistry, what cannot be explained by petrology alone, maybe it can be explained by stress. And we are also close to forecast the timing of magma propagation and predict the onset of eruptions, where and when. So I am absolutely, just to conclude, aligned with the aims of VIPS to combine all the evidence and expertise to find a much better integrated answer to these problems. So thank you very much, everyone, for joining and attending, and I'm very happy to take questions now.
Okay, so we already have a couple of questions in the chat. Anyone who wants to ask a question can add theirs, or just type an X or a Q and they can ask the question directly. So Pablo Gonzalez, do you want to ask the question directly to Eleonora?
Yeah, why not?
Okay.
Thank you, Eleonora. That was a fantastic talk. Thank you for it. As you know, I'm also interested in loading processes on lithospheric scale, and I was wondering that I could notice that you use it point source. How an extended source will change or not your conclusions about the importance of the magma reservoir stress changes and the loading of the volcano. And then a related one is about the time scale of those stress changes. They seem to work in a very different time scale. So is it something you have thought about it?
Yeah, thank you for these questions. So you are partially right. I did use the Boussinesq load, but not just a point. I integrated it on over the shape of a cone on the surface. So it's a cone-shaped load. obviously, even this is a simplification because you don't only have loading stresses like vertical pressure, you also have shear stresses. They are maybe 10%, so they would be important here. I wanted to just make something simple that people could reproduce easily. There are other type of models that can be used, and we are using them like fully analytical with the topography. It's better, especially if you want to have propagation within the edifice, then you need to have the edifice. And we are also using numerical, we are using a lot of this. So if you want to just make a brief point or check your case very briefly, I think Businesq is good. If you want to really have something accurate, then you need to go for something more sophisticated. Then you raise the point of the time scale, and it is a very, very important point, and a point where there is not much work. So indeed, there are very different time scales, loading, unloading. So let's say the loading time scale is such. So one point is compressive stresses and extensional, like really volumetric, they are not dissipated really. They stay in there, and we know this because otherwise we wouldn't have mountain building, we wouldn't have mountain building resisting in the timescales of hundreds of millions of years. So this is something that the crust can hold. What it cannot really hold is shear stresses very much. So they are dissipated. So we have already two different timescales here, which you can possibly model with viscoelasticity, but then there are other processes. There is dissipation, there is new layering coming in. I mean, one thing is if you make a gelatin edifice and then you shoot the dikes. One other thing is if you create a volcano, you don't create it overnight. You accumulate layers and layers and layers. You remove here, you have an earthquake, you have heat, you have, obviously this needs to enter into the study somehow and needs work. Yes. I hope I answered your questions.
It's a very long discussion. Thank you.
Thanks. Luca, do you want to ask your questions?
Yeah, so thanks, Eleonora. That was great. Thanks for participating to this event. So I have two questions. One, when you were speaking about the reservoir, the impact, the relative impact of reservoir and edifice, I was thinking about compressibility. As you know, we think a bit about this now. And I was wondering, perhaps are two different time scales, because by the time the compressibility increased, the edifice has already grown. But what would be the impact to, you know, you have an eruption, imagine you decompress your reservoir, so you get a volatile exsolution and you get something compressible. Is this going to rotate the stress field?
Okay, so everything that happens in the magma, like you say, is very important to decide the moment when the eruption will begin and also where exactly on the chamber there will be a rupture. But I don't think it's very important to determine the trajectories. Although, if you make the dike very buoyant because you put a lot of bubbles into the dike, then the buoyancy will. So one thing I didn't mention is that dikes that are very buoyant tend to care less about trajectories imposed from outside. They are a bit more autonomous. They go their way. While dikes that are small, they really go according to the stress very precisely. So actually, if you bring up compressibility, so I would say there is not so much effect on the trajectories, but there are many other effects that we need to consider regarding the timing of the eruption, for example, or the triggering process of the eruption.
If I can sneak in a second one,
sure.
You know, when you were looking, I think it was the example of Etna, your latest paper, where you use the location of the vents to understand the evolution of the stress field, or you find the best fitting parameter. But I was wondering, do you do it for craters that were active at the same moment, or you do it also in time? Because it will be interesting to see matching
Yeah,
over time how,
Yeah, it was Campi Flegrei.
Yeah. Okay.
Yes, so Campi Flegrei has different epochs, and we see, so if you do this operation of inverting the stresses for Campi Flegrei, you find that the stress changes over time, because indeed the vents migrate inward, and this pattern is basically it's correspondent to a different calibrated stress. We explain this in the study that you mentioned by the filling up of the caldera. So the caldera erupts and brings all the products up, and the excavation of the caldera fills up. And by filling it up, it reduces this ratio between extension and the decompression of the caldera excavation. So you absolutely have to check the history of your edifice in terms of, the position of layers. So we saw in the study that already 20 meters make a difference. Already 20 meters of deposits, they make a difference. I mean, they shift, it depends on the stresses, but they may shift of a considerable amount, I don't know, hundreds of meters, the expected vents at the surface, just 20 meters. You absolutely have to consider the history of the edifice.
Thanks. Now Catherine has a question. Please, Catherine, go ahead.
Yes, thank you. I have a question regarding the shape of edifices and the fact that you have, well, it's dikes or conduits, because you say that it's always dikes that open eruptive access, and then it can become a conduit.
Mm-hmm.
And I was wondering how it works in the context of different type of edifices, with the basaltic one being having a tendency to be elongated along rift zones, and the more silicic one being more axisymmetric, and how it's like the basaltic one stayed dike-like, have a elongated opening, and the more silicic one moved to cylindrical conduit. Can you?
Yeah, so I think your question is very wide, so I will try to make it a bit short. So there is obviously differences in the propagation in basaltic and silicic systems, because basaltic magma is very mobile, it's thin, it can cut very, very efficiently and go all the way. Also, when it accumulates, it can just reach just about the volume for propagation and go. It's much more mobile in this sense. Therefore, it can follow the stress very, very precisely. I would say maybe silicic magma will also do, but it has more pressure of buoyancy. It can is maybe more autonomous, I don't know. And also, once you form the conduit, basaltic magma really can very easily form a new one. And I think silicic magma can less easily find a new one. So we'll tend a bit more to use that is already available. For example, I don't know. It's a very interesting discussion. I think I need to think more to really answer everything by composition. Yes.
Thanks. Janine has a question now, or maybe two.
Oh no, it's the same one. It's just I realised I didn't type it properly. So that was a really, really nice talk, Eleonora. I really like this sort of summary, but also seeing some of the new work from your group as well. But I wanted to ask about the link with volcano observatories and how the sort of fundamental understanding of dike propagation can be useful in a sort of operational sense, and whether you had any thoughts on how that's working so far and how we might evolve models more in that direction so that they're as useful as they could be during a volcanic unrest period?
Yeah, this is a very good question. So the projects we are carrying forward, they are linked to Etna, Cantifegray, and Piton de la Fournaise, because it's with Virginie. So these are the three volcanoes. And our aim, so far there is not yet anything that really could be used unless, you know, you go there and think with them, you know. But our aim is to develop, is to go towards tools that can really be used in times of crisis. And this I mean, the step, this work that my PhD student did is a good step in this. I didn't mention, actually, let me go because I wanted to say something more. Actually, please check these two web pages. Thank you for this, because otherwise I would have forgotten. This is the web page of MEDI, and there are already very good tools. In particular, this CDM weird tree perpendicular dislocation thing is super handy to model all magma chambers in the way you want. And it is all freely available. It's MATLAB stuff. And also go to the GitHub page of Tim Davis, because here you will find all the codes. Now, I don't know if they are already open. Maybe they go open when the paper is accepted. I'm not entirely sure, you can check. But all the codes that the team did for Serra Negra and to develop for this forecasting, they are already available here. While MEDI's codes are a bit more easy to use, these are also easy, but I mean, it takes a bit more programming ability to actually use these ones. So this is maybe the answer to your question. Like we are working so that they become usable. It takes time.
Yeah, that's really great. Thank you, Eleonora.
Thanks. Steffi Burkhardt has a question. Do you want to ask it?
Yes, I can ask it directly. Thank you, Eleonora. I'm glad we recorded this talk, because there were so many things that I need to rewatch and think about. It was very inspiring.
Thank you, Steffi.
I wanted to ask something about dike swarms or sheet swarms, because they're usually thought to represent the stress field, or their trajectories, their shapes. And I think it's quite established that radial dike swarms reflect the load of the edifice. So then I got curious when you said that the magma chamber actually exerts a minor influence in the presence of an edifice. How would you explain the shape of cone sheet swarms?
So I would go for either one of two explanations. One explanation is more according to your work, so that you don't have a full elasticity, you know, because obviously when I talk today, I stayed in that particular domain of very competent rock and elasticity, while there is another full big line of research that also explores granular material or not really consolidated sediments or something like this. So this would be one explanation that goes for the cone sheets, and the other explanation that I would go for is the unloading case. So you actually, and this actually would be good to discuss with you and others. So are you sure there was an edifice there in that case, or actually there was a caldera? Because if there was a caldera, then with the unloading, you created the stress field to actually create a circular, circumferential intrusion by removing a weight that was there before, creating a caldera, creating a collapse structure or something like this. I would say either of the two.
That's really interesting. Yeah, I agree. We should discuss this more. Thank you.
Thanks. So then we have a question from Modesto Gamboa, who's asking, additionally to the magma transport by diking, what other types of transport are there, and how are they related to diking?
This is a very important question because people tend to be a little bit parochial. So definitely when melt pockets are very small and they are produced by decompression, for example, in a hot matrix of rock, they don't migrate by diking. In order to have diking, so they migrate by porous flow or something like this. In order to have diking, you need to accumulate enough magma. So the critical volume is the secret. Once you reach 1 million of cubic meters or something like that, maybe 10 times less, but not really much more less, then you can start a dike and then everything will become very fast. Before that, it will be a slow thing because it cannot work in the same way. Then there are other forms of transport that, as I mentioned when I was talking to Steffi, they work if the medium is less, it doesn't react elastically because, for example, you are in sediments or you are in a granular medium in sand. Actually, you have dikes, sand dikes, even in sand, but I mean, there are gray zones. And I think these gray zones, so what happens between porous flow and diking, what happens at more difficult rheologies. So there are people working on this, but there is not much work to bring these things together and see what are the conditions for the transition from one form of transport to the other and so on. And this, I think, would be very, very needed.
Thanks. Are you okay if we go on a little bit more? We have...
Sure.
Okay, thanks. Tobias Schmiedel has a question. Do you want to ask it live, Tobias?
I can ask it live, yes.
Okay, thanks.
Great talk, Eleonora. I have a question regarding, you showed the model with your ellipsoidal magma chamber and the big lead edifice on top. So the volume in this magma chamber, would it be sufficient to actually erupt the dike towards the top? And what would happen if you would increase this magma chamber volume compared to the size of the edifice?
Yes. So you can calculate it in a way. So you need to see how much. So when the magma chamber feeds a dike, the magma chamber will lose pressure. This is an important point during the feeding process. But there are models, published models, that show how you can calculate how the magma chamber will depressurize during the feeding for the volume that it loses. And it depends on the shape of the magma chamber as well as the volume. The volume is very important because obviously bigger ones will lose less pressure, but they still lose pressure. Then you need to assign a buoyancy to the magma as well, and you need to have a precise stress field. Then, and only then, you can answer really your question is, obviously you can, because it happens. It is a matter of having a bigger chamber, probably. Bigger chamber would help, more buoyant magma would help. And the stress field, you have it, but it can be modified by other processes. It can be calculated.
Okay. May I sneak in the second one as well straight away? Thank you. The diking process in your models, which you showed, seem to always disconnect the dike itself from the actual source at some point. Is that something which happens only on a very large scale? Because on a small scale, when we see magma chambers, for example, in the roof area of the magma chambers, we always see dike-like features coming out of the magma chamber, basically. But is that then the trace of such a big scale dike, which basically is not further exposed than the top, or is that big diking, which loses connection to the magma chamber, just a larger scale feature? Do you know that by any chance?
So I think that it completely disconnects. It only happens at a large scale, I believe. I don't know. But still, even if it doesn't, I think it's very important to include in the calculations also the external stresses, because otherwise you will have only the magma chamber pushing. I don't think this is the dominant force all the time. It's actually, again, I would say lower priority, because most dikes, you see them going laterally and, you know, still draining the chamber. So they are connected. Like the Bardarbunga dike went 40 kilometers away, continued to drain the chamber, caused a collapse. Definitely it's connected, but the force for propagation was also another one, the topography and the tectonic stress. So I think your question is very interesting and cool, because yeah, exactly this connection and what it takes to really detach, and also what it takes to make an attempt to eruption more successful. It's related to the question that you had before. First of all, I think it's not so much about the stress level, but again, you need to calculate really the structure mechanics effects that bring the dike far away, and not just the stress level to break it, but okay, can it continue? Or can I just break it, but then it will stop? So it's all things that are not yet explored very much.
Thanks a lot for answering this.
Thanks. Next question is from Nicolas Vigid. You want to ask it yourself, Nicolas?
Okay, thanks. Great talk, Eleonora. One question is about if in your models, have you considered a strict slip regimen like radial with sigma 2 and sigma 3 with similar values, and how if the magma pressure could have an influence in the dike propagation, if that pressure can modify the trajectory that you can estimate?
Yeah, so I don't think there has been a lot of work in exploring the relative size of the different principal stresses and checking how this really is going to influence the propagation and the pressure of magma. I think this would be an interesting thing to check, you know, to really go and look at the parameters, and because I believe probably if you change very much the ratios between the principal stresses and the magma pressure, you can find different patterns.
Yeah, because, so my question was about this, because in the Andes, we have a lot of strict slip local regimens. So that have a big influence in the volcanic fields. It's very interesting. I'm working on the distribution of these vents. So thanks for answering.
Okay, I look forward to see it one day.
Andreas Mori has another question.
Yeah, so thanks very much for the very interesting talk. That's very nice. There's a lot of input that I'm gonna use also in my work. So I have a particular question, and that's you mentioned just quickly on the fracture toughness that this is a material parameter, and I know that mainly in volcanology, in dike, I call it dike community now. There's a lot of discussion on if it's really a parameter that is material or if it is scale dependent. So my question is one that if I recall right, the codes that Tim uses, they're mostly based on pure what in fracture mechanics is called toughness dominated. So the magma flow or pressure gradients due to the flow inside are not really considered. And so I'm actually working on that. So my question is a bit, if we consider that, how would you see will it change this propagation? If we imagine that we maybe have this magma influence, that then effectively, could we get to something where we say, well, fracture toughness is still a material property, and it's really the relative difference between the pressure drop in the fluid and so on. So what is your take on that? Do you think we need to investigate that to get to a conclusion if it is scale dependent or not, this fracture toughness?
Yeah, I mean, this opens a very important discussion as well. I am all for considering the fracture toughness as an efficient fracture toughness. So I think it's scale dependent, but it's the scale dependence. So my take arises from the fact that when your dike becomes bigger and bigger and bigger and bigger, from a small vein to a very big dike, the process zone becomes very much bigger, and you also have earthquakes. So earthquakes are very big energy sink, and you need to include their effect on the elastic energy. This dike in Iceland caused I don't know how many tens of thousands of earthquakes, and this is all energy that you lose, elastic energy that is released during the propagation, and this is going to increase the toughness of the rock. Every time you have an earthquake, the toughness increases, and this I believe is the reason why you cannot use laboratory values for propagation of dikes. Otherwise, nothing works really. You need to use much more. 1 or 2 orders of magnitude more to make them work, but there is a physical reason for that. Then you bring up the other point, which is about the about the viscous flow in the dike. So obviously this is very important. Also, it determines the timing. I didn't really, I wasn't very clear about this, but in all the models that we do with neglecting the viscous flow, you are not going to have a time for the propagation, the time scale. It's without time scale. You only get a time scale only if you put the viscous flow. The question is whether it will influence the trajectory. I think preliminary results by Virginie and Francesco, both from the laboratory in the gelatin experiments and in modelings that they also do, they say that you do only if the viscosity is very large. I cannot tell you a value now, but it is work in progress that will come out. So they are looking at this exactly. Obviously, the future is to combine these two. And I'm curious to see your work regarding this. Tim actually runs PyFrac all the time when he when he runs his codes. After that, he runs a code which is called PyFrac, which is a code for the fluidodynamics in the dike. He puts as input what he gets out of his trajectory model and the propagation model to see the effects. And it would be great if these two things would come together later on. It's very good work.
Okay. Yeah. So I'm actually working on PyFrac. So that's.
Yes, I guess so. I guess so. So yeah, very good to.
That would be very interesting to put the two things together, honestly.
Yes, absolutely.
Okay. Thank you very, very much. Very interesting.
Thanks a lot, Eleonora. There's not any more questions, but I do have a couple of small questions. The first one is, I was wondering about the source of these dikes. So you kind of seem to say that basically magma chambers are only derivative of dikes, more or less. I mean, you say that vertical chambers are when dikes are favored to move vertically, or seals when they are favored to move horizontally. So I was wondering, in your view, so what roles do these chambers have?
In my view, sorry, can you repeat? In my view,
what is the role of these chambers? Are they just temporary, stationary place for dikes?
Yeah, no, this is obviously a very important question. when the dikes, I mean, here there is all the work done by Catherine and the work that I didn't really go into this. I believe at the very beginning there was nothing, and then some dikes accumulated and created a chamber. Yes, that is how they were born. But then obviously then it's a more complicated than this. Then you have thermal aspects that I didn't go into. You have chemistry aspects that I didn't go into. You have the evolution of the magma, and you have then you have all the work that you are doing where you have something entering from below. I mean, you put it as a straw, but it doesn't really change very much. If you make a dike enter into the chamber, it's the same, I would say. So generally, the view is that magma chambers are the center and they produce everything. I wanted to, bring my contribution and say, look, maybe the external stress is actually contributing very much to deciding where the magma gets stuck during its propagation and where you can really form the magma chamber over the history of the volcano, and you can actually prove it. I'm not saying that I proved it, but I say this idea can be proven because you would have to see that as your edifice becomes bigger and bigger, your magma chamber becomes deeper and deeper. You would see this in the petrology.
Yeah.
You would see that if a volcano creates a caldera at some point, not only the patterns change, but also the chemistry may change in the volcano depending on the conditions. You would see that. So, I mean, it's provable. I'm not, I didn't prove it, but it's provable. And if you do, if you combine all the work that we are all doing, Catherine and me and Steffi and you, and I think we will get to the answers of all these questions. You would need to put the thermal models on top of the dike, and then the geochemistry, and then the convection, and then you have it.
And the petrology.
Absolutely, absolutely.
The petrology.
And so another question related to this, actually. And so I mean, your dikes in your cartoons, they seemed much bigger, more or less, than a chamber. But I was wondering, does the stress distribution inside the chamber have an effect on where the dikes start? And so then maybe...
Chiara, you are wonderful. Okay, so stress distribution inside the magma chamber. Now you get really into more complex things, because obviously a magma chamber is not a cavity filled with a fluid, in spite of the fact that we both put it this way. Yes, it is this mash zone with parts that are definitely rigid and parts that are definitely more viscous, or even pockets of melt. I would say so, yes, but we are, okay, here I can say we are a bit far from actually considering really the stress within the magma reservoir system and figuring out where it will rupture and how it will go ahead. I think we are still the reason I can't see that this will happen this year or next year, that good work will come in this direction, but maybe because I don't know the work that everyone is doing. But I think, yes, it's a very important point.
Thanks. Andreas had another question, I think, if I understood right.
Yes. So, well, it's actually a bit also to go into that, because I think one very important thing is also the source region of this dike. So where do they come from, and how did they emerge? So that's actually going into that. So that one question is if you really say it is a magma chamber, so then the chamber would be filled by some system from the bottom, and then what do you think about this assumption of a point source? Because as I got that right, that's like the assumption which is mostly done so far. What if you talk about on a larger scale, where we would say it's more of a line source? What could we expect there? Would you expect to merge them together, the dikes, or would you see several parallel dikes? Or what's your take on that?
I am not sure I understood the question. So can you repeat?
Yeah. So if I got that right, the idea is also of the simulations that Tim did notably is that it is coming from a point source basically. So we have this point source which then creates an elliptic or a circular magma chamber, and then it's from there where the dike goes on. So, but that is I see that for example for a dike which comes from a volcano. But if we maybe talk about massive transport, well, from further down, so it's not a magma chamber, but it's more like the fluid or where it is the ductile transition.
Okay. So maybe you are asking what could be different ways to model different types of. Okay, this is a very good point. So the point source or spherical cavity or ellipsoidal cavity are more models that I think maybe you are right. They are showing some age. They are becoming old, and we would need models that can integrate conditions where you have, where you really have these MASH models, but you really bring them into deformation models. I think this is, again, not super close in time. I mean, it would be necessary to have more complex deformation models of magma chambers and transport, because they would be very useful. Yes. To some extent, these tools now, this page, if you check in this one, there are point sources of all type in this package of software, and you can use them. You can check the papers of Meti, and you can use these point sources in different ways. He shows it in his papers how you can combine them to model a more extended system. This is a start. I mean, it's a start of an answer. I'm not giving you the full answer because it takes time to develop such an answer as well. Yeah.
No, that's perfectly fine. Thanks. And if I might, maybe just a different question.
Sure.
That's a bit going back effectively on that fracture toughness as a material parameter thing. So I think or when I understood you right, we should more talk about something which is like an apparent fracture toughness. So then it's not a material property, but it depends on a lot of things. And one thing I was asking there, if you see like sublinear micro cracks or like smaller cracks which are parallel to propagating dikes. I think that's the Delane and Polar paper where one can see that as an example. Do you think that these could be explained by taking into account the viscous flow and poroelastic effects, or do you think they are more coming from the process zone? So it's a pure fracture dominated LEFM problem, or do we need to take...
I don't know. It's a good point. I don't know. Maybe so. Let's put it this way: the two things combined, I think it would open a lot of perspective to combine the viscous flow with the external stress and propagation through trajectories that are driven by external stress. Combine these two things. I'm not even sure what would come out. I think a lot of good things would come out, and even explanation for things that we don't know could be explained by that. Yeah. So it's hard to say, it's hard to answer whether these parallel joints, because also when in the models that we do, very rarely we go for checking in the medium whether there is, we don't check that. We could. It's something that one could do, and probably one should do also for forecasting seismicity during the dikes, to also check the patterns and so on. So I cannot tell you because we haven't checked. Could be, but it could also be that the viscous flow really contributes to the stress pattern around the dike very much, if the magma is especially viscous. Yeah, especially.
Okay,
yeah.
Okay, so thanks very much, Eleonora, also for answering all of these questions. It was really interesting, actually. It was a good discussion, I think. I think we can call it quits. Remember, the video will be available on YouTube, and we can keep discussing on Discord if anyone is interested. You should have received the link to join that channel, so if you want, you can join that and continue discussion over there. And thanks everyone for participating. I leave the final words to Janine.
Yes, so thanks very much, Eleonora. It was a really fantastic talk, and it was really nice to be able to have this extended discussion afterwards. So really appreciate all of your effort and time making it a really great seminar. So thank you again and congratulations.
Thank you to all of you for organizing and for joining. Thank you all.
Okay, great. Take care. See you all again soon.
Bye. Thank you.
Ciao, ciao.